The next question. So you have to answer this. A semaphore count of negative n. So if there is a negative value in a semaphore, that means what? It is already told, right? S equal to minus n, then that the queue contains dash waiting process. N waiting process. Understand the question. So how many processes are waiting there? If S equal to minus 3 means what it indicates? It indicates that there are 3 processes is waiting. Okay, that is here n waiting processes are there. Okay. The next question is, a program is located in the smallest available hole in the memory is called as best fit. A smallest available, if there is an available hole is enough, okay, from a set of memory location. So this smallest available hole which should hold my process, that is best fit. Okay. The next one is disk scheduling. Disk scheduling, scan, batch processing, FIFO, time sharing, round robin, and interrupt processing, LIFO, which is already seen, I think. So option C is the correct answer. Synchronizes critical resources to prevent deadlock. So that is semaphore. The dash is one of the preemptive scheduling algorithm. Preemptive, which is non-preemptive, SSN, SSF, and all. So preemptive itself round robin. So round robin or round robin scheduling is a preemptive scheduling algorithm. In order to allow one process to enter its critical section, binary semaphore are initialized to. So that is one process enter its critical section, right? So the binary semaphore is it consists of only 2 values, that is 0 and 1. Okay. It allowing one process means the binary semaphore set to 1. If it is not allowing, if there is no processor there in critical section, then binary semaphore is 0. Okay. So here it in order to allow one process to enter, that is binary semaphore or initialized to 1. The next question, remote computing service involves the use of time sharing and batch processing. So normally remote computing uses time sharing and batch processing. Windows is this is a preemptive operating. Okay, this is a preemptive operating system. And the next one is page making process from main memory to disk. So whatever the things, so main memory to disk. Okay, so I am taken in the value, that's called as swapping. A deadlock in an operating system is an undesirable process? No. It is an undesirable process. It's a definite waiting process. Okay, exactly. It's a definite waiting process. A deadlock in an OS is definitely it is waiting. Okay, the process one, here there is a bus. Okay, this is bus and this bus. Okay, this is waiting for this and this is waiting for this. So a deadlock means a definite waiting process. The next question is the register or main memory location which contain the effective address of the operand is index register. The next question is block or buffer caches are used to. So why we are using block or buffer? Improve disk performance, to handle the interrupts, increase the capacity of main memory, speed up main memory read operation. So what? So disk performance, all the options are what are related to correct answers, but the exact one is why I am using block or buffer caches to speed up my main memory read operation. Okay, so if I am using some buffer or cache so that my main memory will be fastly executed the read operations. The next question is, a file organization component WISAM file is relative record dataset, keyed sequential data set, entry sequential data set. So all the above. This one is, it is related to all. Relative record data set I am accessing, based on the key I am accessing the data set, or based on the entry. So this type of is called as WISAM. The next question is a relationship between processes such that each has some part which must not be executed while the critical section of another is being executed is known as mutual exclusion, which is executed will not be allow others to execute it in the critical section. So such a thing is called as mutual exclusion. How many states then a process be? There are 5 states: new, ready, running, terminated, and waiting states or blocked state. The next one is digital banking algorithm in an operating system solves the problem of deadlock avoidance. Okay, so this banker's algorithm is avoiding the deadlock. Okay, if it is like this, I can avoid the, if I am using the helmet, I can avoid the accident. I can save my, okay, I can save myself. So that's called as an that is the main purpose of digital banker's algorithm in operating system, which is used to avoid the deadlock. The next question is the multi-user operating system. 20 requests are made to use a particular resource per hour. On an average, the probability that no requests are made in 45 minutes. Okay, so 45 minutes, so totally 60 minutes. 60 minutes minus 45, that is remaining as 15 minutes. Okay, this is just remember E minus 15. So on an average, the probability that no requests are made in 45 minutes. So E power minus 15 is the answer. The next question is, on receiving an interrupt from an IO device, what the CPU will do? It halt the predetermined time. It branch off to the internet service routine after completion of the current instruction. Okay, so whenever a CPU receives any interrupt, what happens? The CPU will be immediately go to the particular interrupt service routine after completing of the current instruction. After completion of the current instruction only, it will go to the interrupt service routine. Branches off to the interrupt service, not it won't send it to immediately to the interrupt service routine. It will complete what it has the current instruction, and then it will branch off to the interrupt service routine immediately. The next question, the maximum amount of information that is available in one portion of the disk acts as arm for a removable disk pack without further movement of the arm with multiple head. So first of all, you know, this is a disk, okay, disk platter. So here it is the set of circles, and this circle in this part is called as a sector, and this circle, okay, in this circle is called as a track. So this is a track. First it identify the track where the data is present, and it identify in which sector the data is there. Okay, so the question is, the maximum amount of information that is available in one portion of the disk access arm for a removable disk pack is called a, so I am accessing in this track, so I am accessing all the data in this track. So then that is called as an, this is a just a cylinder of the data. So this is called, this track is called as a cylinder of the disk pack. So it's a cylinder of data. The next one is, consider the logic address space of 8 pages of 1024 words mapped with a memory of 32 frames. How many bits are there in physical address? Consider the logical address space is 8 pages. Okay. So 8 pages, that is 8 pages of 1244 words. So you consider 1024 equal to 2 power 10. Words is also nothing but bytes only. So consider this 1024 equal to 2 to the power of 10. and frames is 32, that is equal to 2 power 5. So physical address bit equal to 2 power 10 into 2 power 5, that is equal to 2 power 15. So 15 bits are required. 15 bits are there in physical address. They ask in logical address, so 8 can be written as 2 power 3, that is equal to 13 bits. 13 bits for logical address. For physical address, frames. Okay, we have to calculate frames plus this memory. So that is 15 bits. CPU, the next question is, CPU does not perform the operation. What it does not perform the operation? Perform data transfer, logical operation. I think the question is CPU does perform the operation. So all the above. So the CPU is perform data transfer operation, logical operation, arithmetic logical operations, control operations, you know that. So the next question is, preemptive scheduling is the strategy of temporarily suspending a gunning process. Yes, before the time slice expires, to allow starving process to run. To allow the starving process? No. To avoid collision when it requests IO? No. So my TP, see for example, process A needs 10 minutes, okay, but the quantum time is, the time slice is 2 minutes for all the process. So A, B, C, D will. So what is the question is, preemptive scheduling is the strategy of temporarily I am suspending this process A, I am outing this A after 2 minutes. So before but my process time need, but A process need 10 minutes. So before its time slice expires, I am just gunning out. That's called as preemptive scheduling. Okay, preemptive scheduling is the strategy of temporarily suspending a gunning process. That is, before the CPU time slice expire, I am just outing that. The next question is, in a round robin CPU scheduling, as time quantum is increased, the average turnaround times increases sometime and it is decreases sometimes. So the correct option is varies irregularly is the correct answer. In a round robin CPU scheduling, as time quantum is increases, the average turnaround time is varies irregularly. For example, it is telling that if you using the time quantum sometimes 5 and sometimes 10, so what happens? The average turnaround time. So it sometimes it increases the average turnaround time, sometimes it decreases. So it is varies irregularly. This is the correct answer. The next question is, resources are allocated to a process on non-shareable. Non-shareable, that is non-divisible, non-shareable. If one is included, other should not excluded. So all the lines will be related to mutual exclusion. Mutual exclusion. The next question is, cached and interleaved memories are ways of speeding up memory access between CPUs and slower RAM. Which memory models are best suited to improve the performance most for which programs? Okay. So what is interleaved memories? Okay, main memories. Okay, this is main memory. Interleaved memory is gap, some gap between one memory to another memory. A gap in main memory. So I am splitting this gap. So I'm splitting the main memory into two portions. Okay. So this is called interleaved memory for speeding up the memory access. So why I am doing this interleaved? Because if I do like this, I can execute this process 1 and here I can execute process 2 simultaneously without any interruption. Okay, so that is the purpose for interleaved memory. So why we are using this interleaved memories? How can I split this at the time of So cache memory is best suited for small loops. So for small in a cache memory, we are splitting into 2 or 3 for small loops. Okay. So, and then for interleaved memory is best suited for small loops. No, interleaved memory is best suited for large sequential code. So this part, a large sequential code will be executed, and this part will be large sequential code will be executed. So option 1 and 3 are true. So cache memory is best suited for small loops, and interleaved memory is best suited for large sequential code. The next question, consider the following page trace. Percentage of page fault that would occur in FIFO page replacement algorithm is used with the number of page frames is 4. So number of page frames is 4. 1, 2, 3, 4. Okay. So 4, 3, 2, 1, 4, 3, 5, 4, 3, 2, 1, 5. So write it down. So 4, write it down. 4 page fault 3, and then 4, 3, 2, and then see, I'll write it in this blue. It's okay. So page is not there. 4, 3 page is not there. 4, 3, 2 page is not there. 4, 3, 2, 1. Okay. So now 4, it's a page hit. Again, it's a page hit. So 5 means which comes first? 4 comes first. So 5, 3, 2, 1. So 4 frames, right? So then 4 is again not there. So I'm changing this. 5, 4, 2, 1. Again 3 is not there. So okay, 5, 4, 3, 1. So again 2 is not there. So 5, 4, 3, 2. So again 1, 4, 3, 2. See how many page faults. See, you can see this. This will become like a wave. So this 1, 2, 3, 4, again it's 1. Then again I have to change this. Right? 5, then again I am 1, 5, 3. So how many page fault? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So number of page fault equal to 10. You got it, this? So this will be like a wave format. So first and second and third, and then again first, again third. If there is again a page fault, means the next will come, right? Okay. The next question is, on a disk with 1000 cylinders, find the number of tracks the disk arm must move to satisfy all the requests in the disk queue. Assume the last request service was at 345 and the head is moving towards track 0. The queue in FIFO order contain request for the following tracks. Assume scan algorithm. So what is scan algorithm says? Scan is move to the one side fully. Okay, move to the largest side fully, or they will give that move to one side. Okay, so move to one side fully, and first point, this is second point, then serve on other side. Okay, just move on one side and serve other side. See, nothing. So scan algorithm, they says that service at track 345. Okay, so now my track position is at 345 and head is moving towards track 0. Now I am moving from 345 to 0 position, and from 0 to the queue in FIFO order contains requests for the following. See, 123, 875, 692, 475, 105, 3. So if the scan algorithm, you no need to draw all these things. Which is highest in this? 874. So go to 874, because I will serve in this 123, 105. Okay, this is 105, 123. So everything will come here itself. Okay, so the largest value is 874. So it will serve here itself 105 and 123 and 376 and 475 and everything, and 692. So you take only the largest value, 874. So 345 plus 874. So the head moment is 9 and 1219. So option B is the correct answer. 1219. Consider the method used by process P1 and P2 for accessing their critical section. The initial values of shared Boolean variables S1 and S2 are randomly assigned. Okay, while S1 is equal to S2 critical section, and I am assigning. Okay, I am not familiar with this. So if anyone knows, write it in the comment box. And here option B is the correct answer. Progress but not mutual exclusion. And the next question, a computer system supports 32-bit virtual address as well as 32-bit physical address. Since the virtual address space is of same size as that of physical address space, if you want to get rid of virtual memory, which one of the following is true? Okay, my virtual memory size and my physical address memory size is also same. That means what? So how much of internet space is there? My system also have that much space. Then what doesn't need? Efficient implementation of multi-user support is no longer possible. It doesn't require it actually, right? The processor cache can be made more efficient. Hardware support for memory management is not needed. Hardware support for memory management is not needed because, so why am I using hardware support virtual? If my physical memory is less than virtual memory, so that I am using a memory management support. If I don't, if my system itself have an huge memory like virtual memory, then I doesn't need any memory management support, right? The next question is the feasible region represented by the constraint of the objective function max. So x1 minus x2 is less than or equal to 1, x1 plus x2 is greater than, so this will come under greater than or equal to 0, x2 is greater than or equal to 0. So objective function, so you consider this, if x1 equal to, make it as an equation. So make it as an equation, x1 minus x2 equal to 1. x1 plus x2 equal to 3. Okay. So when x1 equal to 0, what happened? x2 value is minus 1 and x2 is 0, x1 equal to 1. So 1 comma 0. So this is the points you are deriving from this. So this detailed explanation I explained in the YouTube also, LPP graphical method. So I am directly taking out. So if x1 equal to 0, x2 equal to 3, and if x2 is 0, x1 equal to 3. So just point out this in a graph. So the first line 0 minus 1, 0 minus 1, this part, right? Yes. Correct. Then 1 in x and 0, this is here, and 0 3, and this, no, this part is 0 comma 3 and 3 comma 0. So you see there is no any bounded region with these two equations, right? This is come here, this part is, this one is here and this one is here. This is not bounded in one face. So the answer is, it's a polygon, no it's a point, no it's none of that, it's an unbounded feasible region. This equation is an unbounded feasible region. The next question is, if an instruction takes I microseconds and a page fault takes additional j microseconds, the effective instruction time if on the average a page fault occurs every k instruction is I plus j divided by k. Okay, it's just a formula, remember it. So this is an additional page fault j and k is an average page fault. The next one, which of the following is scheme to deal with the deadlock? So to remove the deadlock, dealing means I want to remove the deadlock. So how can I remove that? By time in, if you inserting some more process, the deadlock will be removed? No. So time out. So based on the time out deal, I can remove the deadlock. The next one, which of the following memory allocation schemes suffers from external fragmentation? External fragmentation is coming under based on the segmentation. So in a segmentation, it is external fragmentation. If it is happen in a paging, it is an internal fragmentation. In a paging, if there is a memory wastage is there, that is called as an internal fragmentation. Fragmentation is a memory port. Fragmentation and in a segment, a particular segment is wasted, that it is called as an external fragmentation. Okay. The next question is, basic path testing falls under. If you are testing basic every statement and everything, that's called as a white box testing. So basic path testing, white box testing, glass testing, everything is called same. The next, if a packet arrive with an m bit value is 1 and a fragmentation offset value 0, then it is called as. So if a packet arrive with an m bit value is 1 and a fragmentation offset value 0, then it is. So here a packet arrives, okay. So m is 1, that indicates that this packet is not the lost packet among all fragments. Okay, fragmentation offset value is 0, so 0 and 8 0, so that is no value is added. See, if so here it is 0, right, offset, here it is 500 offset, so will be added 500, right, this is 1000, so here, so if it is the offset is 0 means what, it indicates this first fragment, right, so option A is correct. The next question, given memory partition of 100k, 500, 200, 300, 600. So draw this memory location. So 100k and this is 500 and 200, this is 500, this is 200 and 300 and okay. So this is 100, right, this is 100k and this is 500k and this is 200 and this is 300k and this is 600k, okay, and process of 212k. So first 212k, where it will come here, so remaining spaces 280, okay, 417, so it will occupy here 417. Okay, and then 112 here itself it occupy. Okay, and then 426. So for 426 there is no space, continuous space in a particular block is not available. So using the first fit algorithm, in which partition would the process requiring 426k be placed? So it is none of this above is the correct answer. There is no space bar 426K, right? So no continuous space is not available. So option E, none of this is answer. The next one is the maturity level used to measure a process. So to measure a process or initial repeatable. So there are a CMM model, capability maturity model. There are 5 levels or that is initial, repeatable, defined, manage and optimize. Just remember this. CMM 1, this is 2, this is 3, 4 and 5. They will ask what is CMM 3 also, that is defined. Okay, just remember it. The problem of indefinite blockage of low priority job in general priority scheduling algorithm can be solved using aging. Yes. So aging is a process where the indefinite blockage, okay, starvation. To remove the starvation, you are increasing the priority of the process. So that process is called as an aging. Okay, see for example. So here the priority of this is process P5, the priority is 20, so it is taking very late, right? And it needs only 2 minutes. It needs only 2 minutes, but it is waiting for the 25 processor. So before this there are 25 processes, you consider that. So low priority process are waiting for the long priority jobs. So to remove that, because of this starvation is happening. To remove that, I am increasing the priority of the process. Okay, the problem of indefinite blockage of low priority jobs in general priority scheduling algorithm can be solved using aging process. So aging is a technique where you are increasing the priority of the process. The next, you try this. If the disk is located initially 32, find the number of disk moves required with the FCFS. So this is answer is 321, right? So if the disk is initially located at 32, first you have to write it in a ascending order. Okay, so 14, then 37, so remove it, 14, 37, and then 65, then 67, okay, remove it, and then 98, 124. Okay, remove all the process added in the timeline. Okay, initially it is 32. So which comes first? 98. Then which comes next? 37. Then 14. And then 124. And then 65. And then 67. So 124 minus 14, that is 110. And here it is 98, 32, 666, 59, here it is 2. So add all the distances. Add all the distances. 84 plus 66 plus 110 plus 59 plus 2. So if you add all this, 61 and 171, 84, 66, 10, 11, remaining 1, 8, 9, 15, 22. So 321 is the answer. The next question, consider the virtual memory system with FIFO page replacement policy. For an arbitrary page access pattern, increase the number of page frames in main memory will increase the page frames. What happens? I told already. Increase the page frame. It also sometimes increases the number of page fault. Always decreases. No, always increases. No, always sometimes increases the number of page fault. Never affect. So option C is the exact answer. Which of the following requires the device driver? So which of the following requires a device driver disk? Okay, using a disk only, CD drive. So we need a disk driver. Okay. The next question is, consider the system having m resources at the same time. The resources are shared by 3 processes A, B, C, which have a peak demand 3, 4, 6. For what value of m, deadlock will not happen? So for this, you just write it down. A need 3 processes, okay, B need 4, and C needs 6 processes. Just write it less than 1. Okay, so 2, 3, 5. 5 plus 3, 2, 2 plus 8 plus 2, 10. 10 plus 1. So if it is an 11 processes are there, deadlock will not happen. See, if there are 10 processes, if there are 10 resources, what happened? If I allocate 2, if I allocate 3 here, if I allocate 5 here, deadlock may happen. If I added 1, 10 plus 1, 11. Okay, no deadlock will happen. For what value? The question is, for what value of m, deadlock will not happen, will not occur. So option 10 plus 1, 11. So greater than 11, you have to choose. So option D is the correct answer. The next question is critical region. Critical region is working set, principality of locality, critical region, mutual exclusion, deadlock, circular weight, weight and singular is an Horus. Okay, 2, 1, 3, 4 is the option. Yes, the next question is, which of the following feature will characterize an that's a mistake, as multi-programmed? So which of the following features will be characterized multi-program? The first option is more than one program may be loaded into main memory at the same time. Yes. So normally what we call as multi-program is more than one program executed in a main memory. The next one is, if a program waits for a certain event, another program is immediately scheduled. Yes, that is also correct. Okay. And the execution of the program terminates, another program is immediately scheduled. Yes. So option A and B and C, all the options are correct. So option D is the correct answer. More than one programs are executed in a main memory at a time, or the programs waits for certain event, another program is immediately scheduled. Okay. So and then execution of program terminates, another program is immediately scheduled. So this is the characteristic of multi-programmed system. The next one is, a thread is a lightweight process. In the above statement, weight refers to, weight means there is number of resources. Weight refer to number of resources. A thread is a simple lightweight process. Okay, if I am doing some job, okay, for example main some int a comma b. So if I am executed as a multi-thread, c equal to a plus b and print c, something like this. So this is simple executed parallelly. Okay, so multi-thread means these are all set of resources. First it executes main and this executes. So it indicates that weight indicates number of resources. Okay, so this is 1 and this is 2. If I am executed if I am split into this process into 4 and execute all the 4 at once. Okay, that's it. The next one is, a virtual memory based memory management algorithm partially swaps out a process. Partially swaps out. Okay. So what it means? That is medium term scheduling. There are 3 types of scheduling: short term and long term and medium term. Short term schedulers are called as CPU schedulers. Short term schedulers are from the state. So there are 5 states, right? Ready, running, terminated, right? So from ready to running, who is giving? Dispatcher. So if it is running after a particular time, if there is any issues, what happen? It is blocked or wait. Blocked or wait. So this, and then blocked will come under ready. Okay. So these are all the 5 states. So partially swaps out. This running process is partially swaps out. This is called as medium term scheduler. This is called as medium term scheduler. Okay. This is called medium term scheduler. Medium term scheduler. Just a long term scheduler is, this is all the students or many students are coming. Okay, from new to, I'm placing in a job pool. A pool is a memory area where I am placing all the jobs in a pool. So all the parents, all the teachers are coming. I make them to sit in a row, sit inside the college, right? So that is called as a long-term scheduler. So this is done by, from new to ready, this is done by long-term scheduler. This is done by long-term scheduler, and this is done by medium-term scheduler. And from ready to running, it's a dispatcher. Okay, who's a principal, PA, or like that something. So this person is called as a short-term scheduler. Short-term scheduler. So there are three types of scheduler: long-term scheduler, short-term scheduler, and medium-term scheduler. From the new set of processes coming, and I am placing in a pool, okay, to the ready queue. Okay, that is done by ready queue. Who is the responsible for the ready queue? Long-term scheduler. And medium-term scheduler is swapping out, in and out. And then dispatcher, short-term scheduler. So new, ready, running. From running to blocked, which is handled by the medium-term scheduler, and from new to ready, set of processes are stored in a ready queue. That is done by the long-term scheduler. And from ready to running, I am sending all the processes to the running. That is done by the dispatcher. That is called as short-term schedulers. That is called as short-term schedulers. And the same question also asked in, already explained this. So go through the previous sum. Assume that the disk height is located at 32 and find number of disk moves. So 98, that is on the same question asked in 2 years. Okay, same question. So if you see the question itself, you can able to, this question is asked 2 or thrice, 98, 37, 14, 124, 65. Even I remember this question I come across. So 321 is the answer. Just you can go through the previous workout. I don't know the number, I just go through it. The next question is, let the page fault service time be 10 millisecond. Okay, page fault is 10 milliseconds in a computer with average memory access time. Memory access time is 20. So I am accessing the memory with 20 nanoseconds. If one page fault is generated for every 106 memory accesses, what is the effective access time for memory? What is the effective access time for memory? So here, so the formula is I plus J divided by K. We studied, right? So I, what? I is this one 20 nanoseconds, okay? Plus J is, every page fault is generated for every 106 memory access, totally 106, and for every page fault there is 10 milliseconds is accessing. So 20 plus, so it will be considered as 100, okay, so it will be 10. So similarly 30 nanoseconds is the answer. So if it is, yes. The next question is, working set model is used in a memory management to implement the concept of, so which is already explained what is working set model. We are grouping, okay, whatever the pages repeatedly coming, that I am set it as one set, okay, that is called as working set, which is coming under principle of locality cache memory. In a cache memory we are using this principle of locality, okay. The next question is, consider the following process with time slice of 4 milliseconds. Time slice of 4 milliseconds, that is quantum time is 4 milliseconds. And so the set of processes A, B, C, D, arrival time and CPU. what is the average turnaround time of this process will be? So what is the average turnaround time? So again, for this process, I have to calculate the Gantt chart. I have to draw the Gantt chart. So Gantt chart, how I have to draw? So based on consider following this time slice. So this is a round robin scheduling. So process first come. Okay. So this is round robin based on, because they gave the quantum time, right? So based on that, I decided this is round robin scheduling. So the first process is A, and 0 to 4 minutes it will be in the. So then B will be in the CPU. So B will be within the 4 minutes, it is in the CPU. And then after 4 minutes, C need 9 minutes. C requires 9 minutes, but only 4 minutes allocated because it has a round robin scheduling. So as the quantum time is expired, it is switched over to the next process, D. So now it requires 16. Okay. So now what is the A? Now again it's coming as in first out A. So it is already 4 minutes completed. Now it is 4 minutes 20. A is completed. Now B is also completed because 4th minute it's completed. And C it is requested. C and D is remaining. Okay. What is C? So 9, here 4 minutes executed. So 9 minus 4, 5, right? So I am C 24. Okay, and then D. So D is how much it requested? So 5 minutes. Here 4 minutes it is executed. Okay. So D required now only 1 minute. D required only 1 minute now. So I am allocating 24 and 25th minute. So if the process is completed before the time slice, if the time slice is 4 milliseconds, but if it completes before its time slice, it just quit the CPU. If its process is over, it just quit the CPU and go on. So 25th second itself, here it quitting the CPU. And what else? So C and D 8 minutes. C needs 9 minutes, right? So C has 1 more minute to execute. So 26. So this is a Gantt chart. So you have to draw this Gantt chart. If you see had this 4 minutes and this 4 minutes, 8 minutes, it is executed. This is called CPU cycle time or CPU burst time. What is the time it required to execute? So now you see what is the average turnaround time. So average turnaround time is equal to completion time. When 8 is completed, 20. 20 minus, so process A. 20 minus burst time, 8 minus arrival time. So 12 minutes it waited. See, 4 minutes, 12 minutes. So you have to take 20 minus burst time, 8, and minus arrival time. So this is the average waiting time for process A. Now, what is the average waiting time for process B? 8. So 8 it is completed, turnaround time. So, but when it's arrived, the 1 minute. Okay, it takes 4 minutes to CPU burst time minus 1. So waiting time is 3 minutes. It enters first minute. So it waits 1 to 4, right? So 3 minutes it waits. So C process completes by 26 minus burst time 9 minus 2. Okay, what it is? 26 minus 11, that is equal to 15. Okay, option D. D when it completes by 25th second. Okay, 25 minus 5 minus 3, 25 minus 8, that is equal to 17. Okay. Yes. Now we calculated all the average turnaround, average waiting time for all the process. Now we have to add this because they asked the average waiting time. So 12 plus 3 plus 15 plus 17 divided by 4. So what it is? 15, 30, 47, 47 by 4, that is equal to 1, 0, 1, 1, right? 11 point. So 1 4s are 4, 1 4s are 4, point 3. And then the remainder is 3, 7 4s are 28, and 5 4s are 11.75. So this is this is an average waiting time. Okay, sorry. What the question is, average turnaround time. You just note down, write down this also. Sometimes this will also ask it. This is average. I written average waiting time. Okay, AWT. I calculated now average waiting time. So what is average turnaround time? Now I am going to calculate. Okay. So just remove this. So write down that also. That is for average waiting time, which is helpful. Sometimes the same question asked for average waiting time or average turnaround. So average waiting time is nothing but, average turnaround time. So average turnaround time is 20 minus arrival time, nothing else. Okay. Arrival time is 0. So it completed 20th second. So this is 8 minus 1, that is equal to, it takes 7 minutes. This is average turnaround time. ATT. Average turnaround time is total time taken to complete its process. Total time taken. So A is completed here. See, 20th minute it completes. But arrival time is 0. We just subtract the arrival time. So 20 minus 0, 20. And then 8. So 8th minute B is completed. Full process. 8 minus arrival time subtract. C is 26 minus 2. That is equal to 24. So D turnaround time is here. 25th second minus 3, that is equal to 22. So 20 plus 7 plus 24 plus 22 divided by 4. So what is the answer? 20, 40, 60, 66, 66 plus 7, 73, right? 93 by 5. So 1 4 saw 4, 32, 8 4 saw 32, and then 1 again 2 4 saw, right? And 18.25 is millisecond is the right answer. So work out this, friends. Work out the same types of questions or repeatedly asked with a little bit modification of numbers. Okay. In the same question, a job has 4 pages A, B, C, D, and the main memory has 2 page frames only. The job need to process its page in a following order. Assume that page interrupts occurs when a new page is brought in a main memory. Irrespective of whether the page is swapped out or not, number of page interrupts in FIFO and LRU page replacement algorithm. So you know already what is FIFO. So first page which is entered, that I have to replace that first out, right? So in the same way, LRU also, least recently used. I have to take the least recently used page replacement. So if you apply and see, the answer will be same. Try on your side. So the option C will come, 9 and 8. If there is any queries on this, you ask me, I will execute. Okay. The next question, resources are allowed to the process on non-shareable. If I am non-shared basis, means that is called mutual exclusion. Okay, allowed the process on non-shareable basis is called as mutual exclusion. And the next question, Banker's algorithm, very, very important. An operating system using Banker's algorithm for deadlock avoidance at 10 dedicated devices. and has 3 processes P1, P2, P3 with maximum resources requirement is 4, 5, 8. Okay, there are 2 states of the following allocation of a device is as follows. State 1, processes P1, P2, P3, device allocated 2, 3, 4. So you just write down this is P1 and this is P2 and this is P3. Okay, so devices allocated is, count how many devices totally allocated. This is for state 1 and this is for state 2. So 2 and 5, this is 8. How many resources we have? 10 dedicated devices and has 3 processors with maximum resource required. So the maximum resource requirement is 4, 5, 8. Sorry. Actually, this question is separately we have to calculate. Okay. So this is state 1. Okay. The state 1, process 2, process 3. Device allocated is, so all are same type of device. Okay. So they are telling that as 10 dedicated devices. Okay. You see. So in a 10 dedicated devices, how many I allocated? 2, 3, 5, 5 plus 4, 9. 9 is allocated. Okay, what is available? Available is 10 minus 9, only 1. I have only 1 resource I have extra. Okay, so now you see 4, 5, 8 is the maximum resource requirement. Okay, 4, 5, 8 is maximum resource requirement. You check now, 2 is less than 4? Yes. But if I allocate this one process to here, it won't satisfy. Okay, I am not able to allocate this 4 resource for P1 also. If I allocate this P2, this only, because only 1 resources are available. If I allocate for process 2, 3 plus 1 became 4 only. And 4 is also less than 5. I am not able to satisfy the process 2 also. And if I given to P3, 4 plus 1, 5. 5 is less than 8. Okay. And I am not able to satisfy that resource also. Right. So process 1, this kind of allocation, this allocation will leads to unsafe state. Okay, this is an unsafe state. But you see this 0 to 4, that is equal to, if you plus this 6, what is total dedicated device? 10. 10 minus 6, now it is available 4. See, this allocation is, okay, if I am allocating 4 to the P1, it completes this job and given this allocated resources. And now I am available 4. So I can allocate now for P2 and P2 job is also completed and I got 6 resources. So and then I allocate to P3, okay, and you will get the 4 plus 6, 10 dedicated resources. So state 1 is an unsafe state and state 2 is safe state. Understood? So work out slowly, you will understood. Okay, it's nothing. So just P1, P2, P3, it is an allocated, add this all, okay. So total allocated is 9. We have only 10 dedicated devices. So 10 minus 9, you have only 1 available. So if you allocated already in this type, we cannot, but the maximum resource, we cannot satisfy this maximum resource requirement for any of the process. We cannot satisfy any of the process maximum requirement. So all the processes in waiting state, in state 1, in these kind of allocation. But if you do this 0 to 4 and available is 6, and the total is 6 and available is 4. Okay, in the process 2 state. So available is 4. So now I can allocate for P1 also, because it needs 4. So I am allocating P1, and then I am taken all the 4 resources. Then I am allocating for P2. Okay, so it will become 6. So I am taken all the P2, its work completes, and I am taken all the allocated resources, and I will give it to the P3, and that will also complete it. So state 1 is unsafe and state 2 is safe. Okay. Yes, a thread is usually defined as a lightweight process because an operating system maintains smaller data structure for a thread than for a process. In relation to this, which of the following statement is correct? Maintains only scheduling and accounting information for each thread? No. Maintains only CPU register for thread? And they're asking which is statement is correct. It doesn't maintain a separate stack for each thread. Okay. So normally thread is executor, stack, register, and scheduling accounting informations or not maintained. Okay. So so just go through this. Thread which does not maintains a separate stack for each thread. Okay. Thread does not maintain a separate stack. That is the correct answer. The next and last question, ready to running. Ready to running means process is, if it is went to ready to running, the process may be dispatched. Okay, the process are doing some action. Okay, just hold it. Blocked to ready. So when I am moving from blocked to ready means what? Request made by the process is satisfied or an event which it has waiting occurs. Okay. Yes. Okay. You see. And then running to block. If I am going to running to blocked means if there is a process running, I am going to the blocked or wait state. What it means? That is the process is preempted. Okay. The process is preempted. Okay. Before the time slice, I am taken out. Okay. Preempted. So this is an so running to blocked. So running to, it's going to blocked means what it is? The process wish to wait, or so this is block, or we can say it as waiting state. So running to block statement, process wish to wait for some action to do another process. So this is 2. Okay. And running to ready. Running to ready means the process is preempted. So it is coming from here and then it is going to ready. That means this is running state. Okay. This is ready state. So that is the process is preempted. And ready to running. After running, what will happen? It is dispatched. Right. So ready to running, after that the process is dispatched. Blocked to ready. So blocked to ready, it is going means it's requested made by a process, it's satisfied. Okay, then if there is a waiting input A, so A value is inputting. Okay, so if you are inputter, the process request is satisfied or an event for which it has waiting occurs, so it is finished. So the blocked state 2, it is going to the ready state. Okay, so this is option this is available in ready to running state. The process is dispatched. Blocked to ready, request made by the process is satisfied. And running to block, process wish to wait for some action. And running to ready, the process is preempted. Okay, yes, go through all these questions repeatedly, and all the best friends, all the best. Good.